I'm going to do a quick derivation or a slow derivation of the range of a projectile. And I'm going to do that by setting up a general problem and solving it algebraically. And we're going to want to figure out how far a projectile goes. I'm going to call that variable r for range. I'm going to want to find out the range of the projectile for an arbitrary speed of projectile launched at projectile angle theta. So this is a general projectile motion problem. We're going to assume the ground is flat, and it's going to come over here and land at the other end of the trajectory. Now, given this, we can solve this using our kinematics equations. We know some basics about the launch speed, so we know that the x component of the velocity is just the speed, v naught, times the cosine of the launch angle, and v naught y is just going to be v naught sine theta for the y component of the launch angle. Since we begin and end our trajectory at the same altitude, which we can call 0, I'm just going to say that y is equal to y naught is equal to 0. And we also know that I'm just going to set that x minus x naught is equal to the range. That's just saying from the beginning to the end in the x direction is what I'm calling the range. So I'm going to give that an extra equal sign as my definition of the range. So starting with the x kinematic equation, I have that x is equal to x naught plus v naught x t plus 1/2 ax t squared. Now this is a projectile motion problem, so I want to make the point that this term is 0. There is no acceleration in the x direction, and I can push the x naught to the other side and get that x minus x naught is equal to the range by our definition up here. And that's equal to v naught x times the time, and I'm going to go ahead and rewrite that as v naught cos theta times t. Now, our general strategy in our projectile motion problems is always going to be then to use the y component to get rid of this pesky t variable. So I'm going to write down y minus, or y is equal to y naught plus v naught y times t, and in projectile motion I'm going to go ahead and say that the vertical component of the acceleration is going to be g downward. So g is the magnitude of the acceleration, downward is where the minus sign comes from. So then I can say that y is equal to y naught equals 0, so I get 0 is equal to v naught y, that's over here, v naught sine theta t minus 1/2 g t squared. Okay, so given that, I can solve this equation for the time that it has altitude 0. And so I get 0 is equal to t. I'm going to factor out a t from this expression because it appears in both terms. T times v naught sine theta minus 1/2 g times t. Now, this t, since we have two numbers that are multiplied together that give us 0, we know that one or the other of them have to be 0. So there are two solutions. It's a quadratic formula, so we get our quadratic equations, so we get two solutions. T equals 0. That makes sense. That's when it gets launched, it's at 0. That's over here. And then we have that t equal, so we get v naught sine theta minus 1/2 g t equals 0. And I can solve that by pushing the 1/2 gt to the other side, multiplying up by 2 and dividing down by g to get that t is equal to 2 v naught sine theta over g. Now I return to the x component and plug this equation in right over here. Or plug the solution in right over there, and I get that range is equal to v naught cos theta times 2 v naught sine theta all over g. So then I'm going to collect like product terms. I get 2 v naught squared cos theta sine theta over g. Now, one thing that's kind of cool about this is that I can use a trig identity. So I know from grade 11 that 2 cos theta sine theta equals sine 2 theta. And that's like one of the only identities I actually remember because I use it right here in these problems. And I get that the range is equal to v naught squared over g times the sine of 2 theta. So there's my arbitrary derivation of the range.